Okay, so I've got this rock that's being dropped off the edge of the cliff. There's an explanation required. It says that this rock is going to accelerate because of gravity. And to make things simpler, we're going to say, okay, we're not going to make gravity be 9.81 meters per second squared. We'll let gravity be a nice round number like 10 meters per second squared, just so that we can like do this as a thought experiment kind of, okay? So we've got gravity 10 meters per second, which is the same as 10 meters per second squared. And we won't usually use that as a value. This is just for head math purposes, okay? We got a motion meter that's been equipped with a speedometer and an odometer. Now, a speedometer is how fast something goes. Odometer is how far, okay? So there's a motion meter that's got both of those reading capacities, and we're going to look at how much time goes by as well as this thing falls. And up to this point, we've been talking about position time and velocity time type information. So this would be like, you know, if you could measure a rock as it was falling. And you can imagine you could do this with some sort of a police setup, you know, like a radar gun or something like that. We could do this. So I got this rock falling. You should never drop rocks off of a cliff. We have a nearby cliff, the Niagara Escarpment, and every once in a while people do drop rocks off the cliff, and it can cause a lot of damage to hikers down below. You don't actually want to do this. But if you did drop the rock off of a cliff, we'd say, hey, at time equals 0 seconds, it's at the top. Time equals 1 second, it's part way down. Time equals 2 seconds, and so on. It's falling faster. Well, is it falling faster?
Yeah.
How can you tell that it's falling faster? Look at the cartoon. Further apart. We saw that on a recent lab. Getting further apart. Must be going faster. We've got a little reading here. The dial is velocity. We've got this little readout here is the time. So the time is being given to us. We've got a position of 0 meters, 5 meters, 20 meters. What do you suppose would happen next? How could we figure out how far it's gone by the 3-second mark? As soon as we start asking about how to predict where it's going to be and how fast it's going to go, we either have to be very good intuitive problem solvers, which you could be, right? And if you want to be an intuitive problem solver, I'd say pause, look away right now. That's fine. But if you want to be an equation problem solver, we've got a toolbox for that at this point, okay? So I could say some variables. I could make a statement like, well, if I'm dropping this thing, V1 was equal to 0 meters per second. If I'm dropping this thing, the acceleration is equal to what? Yeah, you can say it out loud. It's 10. It's 10 in this situation, right? Because we dressed it up that way. We made it nice and simple. 10 meters. And we're not going to think about significant figures here because you can tell the times are all the 1. So I'm not worried about that just now. 10 meters per second squared. Is there anything else we know? No, not necessarily. But if I'd like to know how far this thing has gone by 3 seconds, I could plug in some values, right? Now I think about my equations of motion. And I'll take stock of what I know. I know that I had V2 equals V1 plus A delta T. I had V average equals V1 plus V2 divided by 2. I had delta D equals V1 delta T plus 1/2 A delta T squared. And I'm just kind of rhyming these off. But, you know, like if you're doing all your homework, you're memorizing these things, right? Like this is something that people always say, can I have a formula sheet for the test? Well, I guess so. But if you're not doing your homework and you don't have these things memorized, then you're just slowing yourself down, you know? But yeah, it's a nice security blanket just in case you forget things. V2 squared is equal to V1 squared plus 2A delta D. And then of course we had we wrote it as delta D is equal to V average times delta T. And so maybe not in the same order that they were presented in a note, but these are our 5 equations of motion, okay? And so I think to myself, well, okay, at this moment in time, I would like to figure out how far I've fallen after 3 seconds, or how far the rock has fallen after 3 seconds. Which equation do you think would help us to figure out how far after 3 seconds? Actually, you know what? Just for kicks, let's call them equations 1, 2. By the way, nobody actually just says These are the specific numbers for these equations. I'm just listing them out for conversation's sake. Phoenix, what do you say? Equation 3? So she says equation 3, let's take a look at this. Let's examine it. If I wanted to know how far after 3 seconds do I know V1, this is just me taking stock. I'm checking my inventory. Do I know the time? 3 seconds. Yeah. Do I know acceleration? Yeah. Do I know time? Yes, look at that. Easy. Plug it in. People say, well, could there be a situation where I'd use equation 4? Well, what would be the case? Equation 4, I know displacement, I know acceleration, I know V1, but do I know V2? I don't know V2 at 3 seconds. But as soon as I say that, I think, oh, wait, I bet you this guy's going to ask me what the velocity is at that point. Notice that there's a speed dial and a position reading. I can figure out how far it's going after 3 seconds, but I can also figure out how fast it's going at the 3 second mark. So can you guys please take a minute, beat me to it. Could you beat me to it, please? Find the position using equation 3. Find how fast using equation 4. Okay? Go. Get her done. We'll check in a minute. By the way, this is exactly the kind of thing, but dressed up differently, as the homework from yesterday. We've got nice round values. Remember, we're using 10 meters per second squared for gravity right now, just to keep it simple. You can do all the math in your head that way. Don't forget to square the time. All right, somebody help me out. How far has it fallen after 3 seconds? 9 times 10 times, or divided by 2, yeah. 45 meters, nice. All right, 45 meters it's fallen. And then we say, how fast is it going? Well, now that I have this piece of information that's 45, I actually get to pay it forward into the next formula. I could do that. I say, okay, well, 45 meters. Right, because this is our delta D, this is our acceleration, this is our V1 squared. And again, I can't quite do this one as head math, because V2 is going to be the square root of 2 times 10 times 45. 45 times 10 is 450. 450 times 2 is 900. So it'll be the square root of 900. And you know, I love to insert my units. Really, if I have meters per second squared times meters, the units truly should be meters squared per second squared. Right? Because that's how that meters times meters squared per second squared works out. Sorry, I'll zoom in. I can see some people squinting their eyes. Okay? But then when I square root this thing, somebody help me out. What's the square root of 900? Because I can't do that in my head. 30. 30 meters per second. I'm square rooting the units as well to make them into meters per second again. Okay? So then there's going to be people say, well, oh, Mr. Killens, isn't it truly plus or minus 30? Well, yes, it is, actually. But in the context of this problem, isn't there only one actual answer? And so people talk about admissible answers. Mathematically, the answer is plus or minus. In this case, I think implicitly, I've actually called down positive. And when I say that I've implicitly called down positive, what I mean is I've called the displacement a positive value. I've called the acceleration a positive value, and it went down 45 meters, positive. It accelerated downward, positive. So I've already actually assumed this. I just didn't formalize it. So when I write this out, I'm actually saying that it's positive 30 meters per second, which in this case means down, based on the reference frame that's been given, okay? And so I could go back and I could say, okay, well, if I was going to fill in this template, really, I say, all right, well, it's gone down 45 meters. I'll write the number 45 there. it looks like that was a digital readout, and I would point the analog dial at 30 meters per second, point it right there. And we should be able to do all the rest of these things as well. And so what I want to do is I want to give a couple of extra answers. I want to suggest that if you do it all right, you can check your work. This one should be at the 80 meter mark. This one will be at the 125 meter mark. And this one will be at the 180 meter mark. And I want you to make sure you can mathematically get those answers. But before we do that, can I get one more? Hey, let's do it. Let's figure out how fast it'll go at the 180 meter mark. Let's just see if we can do it, okay? So at this final position, I'd like to know how fast is it going when it strikes the ground. If this is apparently, this is a 180 meter tall cliff. We didn't know till just now, okay? So this is new information. We just figured out that after a 6-second fall, 180 meters. Go. Figure out how fast this thing is going to go when it smacks into the ground. Think about what equation you're going to use. Yeah. Yeah, these are, I mean, this is me kind of spoon feeding it, but the quiz will be questions exactly like the homework. I'm never out to get you. Okay. This course is challenging enough. I don't need to try and make it hard, right? So find out how fast it's going when it strikes the ground at the base of our 180 meter tall cliff, which we were never told until just now. And actually, oh, that's interesting. You could time how long it takes for a rock to hit the ground from a cliff, if you were able to do such a thing. And without a meter stick, you could measure how tall the cliff is. You could do this, right? Maybe you'd use a different gravity, maybe not 10, maybe you use 9.8 or something like that. But you could time a rock fall and figure out how tall the cliff is. Just make sure there's no hikers at the bottom. Maybe that'll be the next thing you do. Next time you go out on a little date or something like that, it's always good to get dating advice in physics. Take a picnic, go to the edge of the cliff, say, darling, I bet you I could tell you how tall this cliff is just by timing this rock. And a little bit of paperwork later, that special person will just fall in love. They'll swoon. They're like, wow, wow. That's the kind of person I want to spend the rest of my life with. Physics, baby. It changes lives. Hold on. All right. Somebody tell me. Somebody I haven't heard from in a while. How fast is this rock going when it smacks into the ground? Yep. What's that? 600? Anybody else get 600? 60. Anybody get 60? Oh my goodness. I got news for you. If it's going at 600 meters per second, it just broke the sound barrier. We should expect sonic booms by the time it hits the ground, okay? But yeah, so and actually that helps with some number sense, you know? If it's anywhere in the mid 300s, you've broken the sound barrier, and that should be like pause for question. But yeah, 60 meters per second, that's good. 60 meters per second. And actually, you know what? This is a good thing to consider, and why we don't toss rocks over the edges of cliffs when we're trying to impress people at those romantic picnics, right? Because neglecting for drag, that's going to really hurt, right? Doesn't matter how small the rock is, even a pebble. We don't really, I know there is drag, but it's still going to hurt. Wow. Pennies from above aren't going to kill anybody, but they will hurt.